The second section in the chapter on fluid mechanics in Young and Freedman's University Physics is on pressure in a fluid. This is a rather long section, but basically pressure is the force per unit area in a fluid. It's not the same as force. Force has a direction. Pressure doesn't have a direction. So force is a vector, whereas pressure is a scalar. But at any particular point, pressure is the change in fluid per area. But if it's constant, if the pressure is uniform throughout a liquid, say, or throughout the air, then basically we can say that the pressure equals the force over a certain area. Force per unit area, that's pressure. So what kind of units are we looking at here? Well, we've already met the Pascal in an earlier section of Young and Freedman's physics. A Pascal is basically 1 Newton of force per square meter, because area, not volume. In meteorology, weather kind of discussion, we talk about a bar or a millibar. 1 bar of pressure is basically 10 to the 5th power pascals, 100,000 pascals. So a millibar is going to be 1/100th of 100 pascals. So those are meteorological terms that are similar, and of course the atmosphere is roughly the same as 1 bar, but not exactly. So 1.013 bars is an atmosphere, or 1.013 times 10 to the 5th pascals. Okay, this is not hard so far. Varying pressure with depth. They derive this formula. I won't do it. You can see their derivation in the section or in whatever book you're doing. But basically, the incremental change of pressure with regard to height is going to equal the negative density times gravity. Again, they divide it. If you want to, they derive it. If you want to see the derivation, go to your textbooks. But this is the formula, basically, that you'll want to use to look at the how to find the change of pressure per time in an incremental sense. If you integrate this particular formula, it implies that if you have varying depths in a fluid, say in the ocean or whatever, the pressure at the top, minus the pressure at the bottom, the difference in pressure is going to be the density times the gravity times the difference in height, y2 minus y1. So that formula is helpful when you have some kind of a fluid, gaseous or liquid, that has varying pressures at different heights. If you want to figure out this, kind of take this formula and apply it to the depth you're in a liquid, say, substitute P0 for P1, and you basically have that the pressure at some depth equals the pressure at the surface plus the density times the gravitational constant, 9.8 meters per second squared, times the height, where basically h is y2 minus y1. Okay, so formulas basically to look up or memorize. Pascal's law, Pascal lived in the 1600s, is that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and to the walls of the containing vessel. This is the basis of hydraulic lift kinds of things, because what this means is that you can put a certain amount of pressure on a liquid on one end of a tube, and then that same amount of force is going to be distributed to the air, to another part. Let's say you can lift a car, as it were, by putting a small amount of pressure on one smaller area. So let's say you put a force on a smaller area. That is going to distribute the same ratio of force to a larger area. So you could lift a car, because you have an open area over here that's big and can suit a car, by putting a amount of pressure on a smaller area over here. This is how a dentist chair goes up, or a barber's chair, or you put up a car so that you can get underneath and change the fluid. Hydraulic lifts use this principle because the ratio is the same. If you put a smaller force on a smaller area, it's going to end up applying a larger force over a larger area over here. That's Pascal's law. Okay, absolute versus gauge pressure. So when you talk about tire pressure, 32 pounds per square inch or whatever, or pressure in a tank that's exposed to the air, usually we're talking about gauge pressure. So when I talk about 32 pounds per square inch in a tire, we mean 32 pounds per square inch above the atmospheric pressure. So if the pressure in a tire is just equal to the external pressure, it's not going to hold a car up. And so gauge pressure is basically the pressure minus the surrounding air pressure. Absolute pressure is when we're talking about the total pressure, which includes the surrounding air pressure. Okay? Again, this is all kind of definition stuff mostly, and some fundamental principles. So, final part of this chapter, long chapter, talks about some basic pressure gauges. So the manometer measures air pressure by a tube that's open on one end and closed on the other. So you might have a kind of U where the top of the one U is open to the air, so you have that equal pressure going in there, and it's going to measure the same amount of pressure over here where it's closed. So manometer is a way of measuring pressure. The barometer also measures air pressure, but it usually has a closed tube and then maybe in an open dish, and a lot of times a barometer will use mercury, for example, and so the pressure of the atmosphere on the mercury in the dish will cause the mercury to rise in the tube that's closed. And so a torr, named after a scientist named Torricelli, a torr is basically, one torr is 1 millimeter of mercury based upon pressure. Well, long section, lots of definitions and stuff, but you can see that we've hit a part of the book where basically people for hundreds of years have been doing stuff with this part of the book. And so there you have it, pressure in a fluid.